Now, let's learn about the technologies introduced by the 5G air interface to cope with these security threats. The first security technology is the two-way authentication between 5G UEs and the core network. In a mobile network, the core network needs to verify whether a UE is legitimate. In early mobile network, for example, 2G mobile network, only UEs are authenticated, and the UEs do not authenticate the network. In other words, the UE always believes that the network is legal. Consequently, fake base stations appear to form a fake network. The UE does not authenticate the network, and the fake network may steal user information. This is a security vulnerability. This security vulnerability is actually fixed by the 5G network. The 5G network implements two-way authentication between UEs and the core network. Therefore, the fake base station cannot exist in the 5G network. Actually, this type of two-way authentication has been available since the 3G network. Two-way authentication is used on 3G, 4G, and 5G networks. In this case, there is no security threat from fake base stations. However, downgrade attacks may still exist. That is, there may be a fake 2G base station. It enables a 5G UE to fall back to the 2G network in some cases. After 5G UE is connected to the fake base station, user data may be stolen. This security threat exists. This is because it is sometimes inevitable for a UE to fall back from a 3G, 4G, or 5G network to a 2G network and set up a connection to a fake base station. This security threat does not come from 3G, 4G, or 5G, but from 2G. Then, how do we solve this problem? Currently, there is no perfect solution to this security threat. Some of the existing solutions prefer to prevent 5G UEs from using 2G networks. In this way, the security threat is eliminated. For example, we can disable the 2G network on our 5G UE. In this case, the UE falls back only to 4G or 3G network. Alternatively, we can modify configuration data on the core network to prevent UEs from falling back to 2G networks. In this way, the security threat caused by connecting the fake base station can be avoided. These solutions are not perfect. In some areas, only 2G base stations are deployed to provide coverage. If a fallback to 2G networks is disabled for a UE, the UE may not receive any signal. Two-way authentication is used for the air interface of the 5G network to protect the 5G network from being threatened by a fake base station. It is the first security technology used for the air interface. The second security technology is SUPI encrypted transmission. What does SUPI mean? It is short for Subscription Permanent Identifier. Before learning about SUPI encryption, let's take a look at this question. How does a network work without SUPI encryption? On 2G, 3G, and 4G networks, the permanent identifier of a subscriber is not called SUPI, but IMSI. IMSI is short for International Mobile Subscriber Identity. This number is written in the SIM card. It is the unique code of the SIM card in the world. As a user's fundamental identity, it is as sensitive as our ID card number. Therefore, we should try to avoid using this number in normal cases. To prevent the IMSI from being disclosed during transmission, a temporary mobile subscriber identity, TIMSI, is used for mobile services. However, in some scenarios, the TIMSI may not be identified by the network. For example, assume that you are a roaming subscriber and just come back from abroad, and your TIMSI is allocated by a foreign network. When you access the network using the TIMSI allocated by the foreign network, the local network cannot identify the TIMSI. In this case, the system asks your UE to report the IMSI. which is your absolute identity number. Your UE then transmits the MC in plain text over the air interface, which may cause the MC to be intercepted and disclosed. This is the method of 2G, 3G, and 4G networks. That is, in some scenarios, MCs are transmitted in plain text, which may cause data leakage. The 5G network has fixed this security vulnerability. The permanent number of 5G subscriber is named SUPI, which has the same meaning as MC. The SUPI will not be directly transmitted in any scenario. The SUPI is always encrypted into SUSI before being transmitted. In other words, the SUPI will never be transmitted in plain text over the air interface. In this case, encrypted numbers may be intercepted. However, it cannot be decrypted or stolen. In this way, the vulnerability of intercepting the MC in plain text has been fixed. This is the second technology introduced for the air interface, that is, SUPI encrypted transmission. The third security technology used on air interface is 256-bit encryption key. Before learning about the 256-bit encryption key, let's take a look at the 2G, 3G, and 4G networks. On 2G, 3G, and 4G networks, data is also encrypted before being transmitted over the air interface. However, their encryption keys are 64 or 128 bits long. Currently, 64 bits are used. Currently, 64 bits are not secure enough. A 64-bit key can be cracked by a supercomputer within 3 to 4 seconds. 64-bit keys are used by 2G networks. Currently, if the supercomputer with the most powerful computing capability is used, the 2G encryption key can be cracked within several seconds. To enhance security, 3G and 4G networks use 128-bit encryption keys. If a 128-bit encryption key is used, it may take trillions of years to crack the key using the current supercomputer. Currently, 128-bit encryption keys used by 3G and 4G networks are secure keys, and supercomputers can hardly crack them. However, as we know, quantum computing technologies are emerging now, and quantum computers may appear in the future. If a quantum computer is used to crack the key, 128-bit key may be cracked within seconds. Therefore, regarding that quantum computers may appear in the future, the 128-bit encryption key used by 3G and 4G networks is insecure. To further enhance security, the 256-bit encryption key is introduced in 5G network. Even using quantum computers, it will take trillions of years to crack a 256-bit encryption key. In other words, it is almost impossible to crack the 256-bit encryption key. In this way, brute force cracking using quantum computers becomes useless for 5G encryption in the future. The 256-bit encryption key is the third security technology introduced for the air interface. What is the fourth security technology introduced for the air interface? It is user plane integrity protection. Let's learn about integrity protection first. Integrity protection ensures that information received by the receiver is complete and has not been tampered with. If information is tampered with, it indicates that the information is different from the original information. Integrity protection ensures that the receiver can identify whether information has been tampered with. Integrity protection has been performed on the control planes of 3G, 4G, and 5G networks. All signal messages have been processed with the integrity protection. If a signaling message is tampered with, it can be identified. However, integrity protection is not performed for user data on the user plane of 3G and 4G networks. In other words, if information transmitted on the user plane is tampered with, the information cannot be identified because integrity protection is unavailable. This security vulnerability has been fixed in 5G. An experiment has ever been done in a lab. In the experiment, user information is tampered with in the lab, causing users to access unauthorized servers and exposing users to security threats. This security vulnerability has been fixed in 5G. Integrity protection is also performed on the user plane of 5G networks. If user plane information is tampered with, the receiver can identify the tampered information, regardless of whether the information comes from the network or a UE. User plane integrity protection is the fourth security technology introduced for the air interface.